let's suppose we have some set R, a set R, and R satisfies the following conditions. Satisfies the following. I'm just telling you this. I have a set, I'm calling it R, and I'm telling you that it satisfies the conditions that I'm about to write down. And so that I don't have to keep writing this, I'm going to say this is for all A, B, and C in R. Number 1. R forms an abelian group. Under the operation addition. Under addition. And we're going to denote that with just a plus sign. And if it's been a while since you've taken group theory, or maybe you haven't taken group theory, which I highly recommend you do before starting any of my ring theory videos, this one statement right here tells us 5 things, and I'll use blue for this. 1, it tells us that R is closed under the operation addition. So A plus B is an element of R. And again, this is for all A, B, and C in R. 2, tells us R is associative under addition. So A plus B plus C is equal to A plus B plus C. So it doesn't matter the order in which you add any 3 elements of R. 3, we have the existence of an identity. And since we're always dealing with addition here, we're going to denote the identity with 0. And if you're coming from a group theory class, you've probably seen this as E for any kind of abstract group. But here, since we're always using addition, we're always going to denote it with 0. So there exists 0 in R, such that A plus 0 is equal to 0 plus A, which is just A. Number 4, we have additive inverses. So for all A in R, there exists a additive inverse for A, which we're just going to denote with a negative symbol in front. It's not really negative A, it's the additive inverse for A, that we just use the negative for it. So there exists a negative A, or a additive inverse A in R, such that A plus the additive inverse of A is equal to the additive inverse of A plus A, which is equal to 0, our additive identity. And lastly, number 5, since this is an abelian group, we know that A plus B is equal to B plus A. Alright, so far, I've just told you I have a set R, and it forms an abelian group under addition. On top of that, I'm going to say that R is closed under the operation multiplication. Under multiplication, which we will denote with either just a dot, or sometimes you'll see a star. I'm going to use the dot for my videos. Now, if you just come from a group theory class, this probably seems a little weird. We have a set R, and we're imposing 2 different operations on it at the same time. That might seem a little strange to you, but hopefully after I get done defining this, and I'll do an example, and hopefully you'll realize it's not really that big of a deal. So this statement tells us that A times B is an element of R. Again, for all A and B in R. 3. R is associative under multiplication. Associative under, I'm just going to write mult, short for multiplication. Mult. And that tells us that A times B times C is equal to A times B times C. again for all a, b, and c. And lastly, since we have two operations here, we kind of need some sense of how they're going to interact with each other. So we're going to have the distributive property. Which tells us that a times b plus c is equal to a times c plus a times b plus a times c. And it also works the other way around, so a plus b times c is equal to, gotta get this right, a times c plus b times c. Alright, so I'm telling you we have a set R. It forms an abelian group under addition. It's closed under a second operation, multiplication. It's associative under multiplication, and the distributive property holds. So if all of these hold true, we say that R is called a ring. R is called a ring. Now let's do a couple examples of these, so hopefully you'll figure out, you'll see what I'm kind of talking about here. So examples, and I'm going to walk through the first one. I'm not going to prove it, but I'm going to walk through each of these steps, and hopefully you'll see what all this really means in an example. And then I'll give you other examples, and I encourage you to kind of go through them on your own, or at least one of them. So the first one is the integers. Okay, so let's go through this. So if you've come from a group theory class, hopefully this first one seems pretty obvious to you. The integers do form an abelian group under addition. So if we take any two integers and we add them together, we're going to get another integer. So for instance, 2 and 3 are both integers. If we add those together, we get 5, and that's another integer. Nothing special about 2 and 3. This will work for any integers. There's no way to add two integers together and like get some kind of rational number, or some kind of matrix or something. That's just weird. The integers are associative. So if we take 2 plus 3 plus 5, that's the same thing as 2 plus 3 plus 5. Doesn't matter the order in which you add these, it's going to come out to the same sum. The additive identity is just plain old 0. So if you take 0 and add it to any integer, let's say 7, you're going to get 7. That works for any integer. Additive inverses, let's say 10. We want to add something to 10 to get our additive identity 0. Well, we're just going to add negative 10. And this time this really is like the negative number. Like here I was saying the additive inverse, and I was just using the negative symbol. This really is negative 10. So 10 plus negative 10 is going to give us 0, which was our additive identity. Doesn't matter the order in which we add any two integers. 2 plus 3 is the same thing as 3 plus 2. It works for any integers. They're also closed under multiplication. So if we take two integers, 5 and 3, we multiply them together. These are two integers. We're going to get 15. That's another integer. Nothing special about 5 and 3. This is going to work for any integer. Again, there's no way to multiply two integers together and get something crazy like a complex number or something. That's just not going to happen. They're also associative under multiplication, again, just like right here. It's going to work the same exact way. 2 times 3 times 5 is equal to 2 times 3 times 5. These are both 30, looks like. Distributive property. So 2 times 3 plus 5. Well, that's 2 times 8, 16. The other way around, let's say 2 times 3 plus 2 times 5. That's going to be 6 plus 10. 6 plus 10. And again, that's 16. So these are the same thing. And nothing special about these numbers. You could pick any integers here and it's going to work. So I just showed you, I just kind of quickly waved my hands at this, but the integers form an abelian group under addition. They're closed under regular multiplication. They're associative under multiplication, and they have the distributive property. So we could say that Z is a ring. Okay, a couple more examples. The rational numbers also form a ring. The real numbers form a ring. Even the complex numbers form a ring. If you want to get a little more crazy, you could say the set of all 2 by 2 matrices whose coefficients come from really any of these. We could say Z, since we just walked through that. So the set of all 2 by 2 matrices whose coefficients are integers will form a ring. If you want to get a little more crazy too, you could say Z sub n. This is the set. If you haven't seen this before, this is the set 0, 1, ... up to n minus 1. And this one's a little different because the operations aren't just plain old addition and multiplication. They're addition mod n and multiplication mod n. But it works pretty much the same way. A couple things that I kind of want to go through that things that are not required of a ring. Things not required. In other words, things that I did not mention in the definition of a ring. If you notice, I said that addition right here is commutative. Nowhere in here did I say that multiplication is commutative. So if you have a ring, it does not need to be commutative under multiplication. So multiplication commutative. Now, we don't have to have multiplication to be commutative in order to be considered a ring, but there are rings out there that are commutative under multiplication. For instance, Z. 2 times 3 is the same thing as 3 times 2. So we could say that if a ring is commutative, we just say it's a commutative ring. So we could say that Z is a commutative ring. Okay, now 2. Let's go back to our definition. Again, right here, I said that there is an additive identity. In other words, an identity for the operation addition. I did not say that there has to be an identity for the operation multiplication. So, a multiplicative identity, in other words, multiplicative identity. Now again, you don't need a multiplicative identity to define a ring, but there are rings out there that do have multiplicative identities. For instance, the integers. If you take 1 times any integer, 3, you're going to get that integer again, 3. This 1 doesn't really change anything. So a ring that does have a multiplicative identity, we could say that there exists, and just like we, with the additive identity, we denoted it with 0, we're going to denote the multiplicative identity with 1. So there exists a 1 in whatever ring you're talking about. And note that this isn't always the actual number 1. We just denote it with a 1, kind of like in group theory, you denoted things with E. But that's, with a specific ring, it's not really like the calculus E. It's E just represents whatever your identity is. So there exists a 1 in R such that 1 times A is equal to A times 1, which is just equal to A. Okay? This 1, we usually don't actually say multiplicative identity. we call it a unity. Unity. And we could say that you'd actually say that R is a ring with unity. And again, we already said that the integers is a ring with unity, so we could say that Z is a commutative ring, actually. Commutative ring with unity. Okay, and last one. Let me scroll down a bit. This is getting kind of low. Since we don't need a multiplicative identity, we certainly don't need multiplicative inverses. I'll just write mult inverses. That's kind of sloppy, sorry. Inverses. So, if you do find a ring that does have multiplicative inverses, you would say that for all A in R, there exists and we denote multiplicative inverses with a -1 power. And so for all A in R, there exists a multiplicative inverse for A in R also, such that A times A inverse is equal to A inverse times A, which is equal to our multiplicative identity. So really, you can only have multiplicative inverses in a ring with unity, because, I mean, there's no other way to define it if we don't have a multiplicative identity or a unity. Also note that there are rings out there that only some elements of the ring have a multiplicative inverse. For instance, the integers. Most integers don't have a multiplicative inverse. So for instance, 3 times something is going to give us 1. Well, that something would have to be 1/3, but that's not an integer. So for most integers, there isn't a multiplicative inverse. However, -1 has a multiplicative inverse. It's actually itself, because -1 times -1 gives us 1. So for instance, -1 is actually the only element of the integers that has a multiplicative inverse. So you don't actually have to have all multiplicative inverses. You can actually have just some elements, or maybe most elements. It doesn't have to be all. And lastly, the technical term for multiplicative inverses is a unit, not to be confused with unity. Unit. And lastly, I'd just like to say that in the description of this video, I'll be posting a couple practice problems for you to do if you'd like. And in the next video, I will post at least solutions to some of them, also in the description.